All right, welcome back. Let's get into Chapter 18. Chapter 18, we're going to be discussing wideband oxygen sensors, and we're also going to be discussing narrowband oxygen sensors again so we can look at the differences between the two. So let's start with conventional oxygen sensors. Conventional oxygen sensors have been a mainstay in the automotive industry for like several decades, going back to 1976, so it's even more than several decades. Bosch first introduced them on Volvos. I'm reading off this little cheat sheet here on the 240 and 240, the 240 and the 260 models. A narrowband oxygen sensor um, was implemented way back then, and so that's at the very early days of electronic fuel injection, and basically like the time when we were inventing technology, but it wasn't necessarily like put on a lot of vehicles. So Honda was actually the first to start using the wideband oxygen sensor, and that happened as early as like 1992. And so wideband oxygen sensors have been around, the technology has been around for a long period of time, but it hasn't actually been utilized mainstream by manufacturers until really like the mid 2000s into like 2010. So once you get a vehicle that's around 2010, you can pretty much guarantee that it's going to have a wideband oxygen sensor and not a narrowband. And when you're looking at older fuel injected cars, like way back in the early days, the technology was around in 1976, and so your OBD1 1989 Chevy Silverado had a narrowband oxygen sensor on it. So wideband oxygen sensors, in the text we're going to look at this, is one of the first things that comes up right here. Wideband oxygen sensors are referred to by multiple names, where your narrowband is typically just called an oxygen sensor. So your original oxygen sensors were non-heated. They were your single wire oxygen sensors, single wire, maybe two wire oxygen sensors that just had the sensing circuits coming from the sensor back to the computer. Your O2 is what that's called. Your O2S, or excuse me, your HO2S is your heated oxygen sensor, and that's where you saw three wires and sometimes four wires. Wideband oxygen sensors are referred to by multiple names. And so in the text they talk about that is, wideband oxygen sensors, broadband oxygen sensors, wide range oxygen sensors, AFR sensors, air fuel sensors, linear, wide range, all that stuff. The important part there to note is that manufacturers in service information will give you that information. And so on your scan tool, you might not see it listed under something you're familiar with. It's very important to understand that you need to reference service information when you're a new technician and you're not quite sure when looking at scan tool data where the oxygen sensor data actually is, because it might be called an AF sensor, it might be called AFR sensor, a whole bunch of different things that could be listed out. And so if you're having problems finding wideband oxygen sensor data and you're not sure which PID it actually is on the scan tool, take a minute and go back and reference service information and read up on the descriptions. Narrowband oxygen sensors only have the ability to cycle from rich to lean. You can't see anything outside of stoichiometric. All you know is that you want rich and you want lean. And so there's disadvantages to using a narrowband oxygen sensor in today's day and age because we have much stricter fuel economy standards and emission standards that manufacturers need a better sensor in the exhaust stream in order to more accurately determine what the actual air fuel ratio is, so they can tune that engine to run a little bit richer or a little bit leaner depending on the scenarios that are at hand. So we need to look at wideband oxygen sensors and compare like voltage, for example. How do they actually look on a scan tool? So your narrowband oxygen sensor operates in that 0 to 1 volt scale. It's a little bit different than how your scan tool data is going to look when you're referencing wideband data. So for example, let's take a look at page 18 and have a look at Toyota's voltage range. So 3.3 volts on a factory scan tool, it can be an Altel, it can be a Snap-on, doesn't matter. As long as it has factory capabilities, 3.3 volts is what the scan tool is going to show you in reference to stoichiometric. If you're using a generic scan tool, just your simple Harbor Freight code reader, it's going to display completely different. And it might not even look like this. It might, for example, the book is saying 0.66 volts, but that scan tool might not reference it even in that way. It might be a voltage that's a little bit different from there. So your factory scan tool is going to reference voltage on the scale. And what you have to understand is this is a calculated voltage. The computer in the car is not actually watching voltage. What it's watching is the current that's being applied to the sensor and the reaction, and it's using voltage as a display mechanism in order to display what the air-fuel ratio is. So this voltage is not actual voltage that's coming out of the sensor. This voltage on a factory scan tool is going to be voltage that is used to display a corresponding air-fuel ratio, where your generic scan tool might actually put it in a different scale, and that can be a little bit confusing if you're looking at service information and you're seeing in service information that on your scan tool you should see around 3.3 volts, and you're using a generic scan tool, and it's going to look nothing like that. It might even look something similar to a narrowband oxygen sensor, where you're at 0 to 1 volt range. And so that can confuse you as a technician when you're a new technician, especially if you don't understand that theory and that principle. With the modernization of the internal combustion engine, if we take a look at advancements such as direct injected engines, where we put the injector actually inside the combustion chamber, or variable valve timing, variable camshaft duration now with the Hyundai, we have engines that are capable of exceeding the boundaries of past generation engines. And so one of the advantages, for example, with direct injected engines is we now have the ability to run a leaner air-fuel ratio. And if you maybe do some Google researching for now and take a look and see how a direct injected engine works, it actually has the ability to spray the fuel at various points of piston travel. And piston design, in many cases, is different as well, where there's a cup maybe in the middle of the piston, and if I fire that fuel at the last second, I can squirt that fuel into that tiny cup where I maybe have an overall displacement size that's reduced by 75%. And so I can run that air-fuel ratio a little bit leaner, also because I have better atomization taking place. When I'm pushing that fuel into the cylinder at 5,000 psi, you have an instantaneous atomization of the fuel. And so Hondas had the ability, but they were expensive, they were confusing for technicians, and they frankly just weren't necessary for the technology that was inside of an internal combustion engine at the time. There was no real need to have an oxygen sensor that had the ability to see anything other than stoichiometric, because at the federal level with your EPA, emission standards were much different at that time as well. And so they had to add catalytic converter monitoring, for example, and so all they did was just take another narrowband oxygen sensor and put it downstream. But when we got into advanced tech, when we started making these engines more fuel efficient, we really saw that happen in like the mid-2000s with manufacturers coming up with variable valve timing, for example. In order to achieve the full benefit of these new engine designs, we had to have the ability to tune that air-fuel ratio accurately beyond stoichiometric. And so if you look at a gasoline engine that's running down the interstate, for example, cruising down the interstate at 70 miles an hour on a flat Illinois road, that vehicle only needs maybe 20% of its actual horsepower. So if it can produce, 200 horsepower, it might only need 40 horsepower to run down the interstate. And so there's a direct correlation between gasoline injected and horsepower out. But there were limiting factors in previous internal combustion designs that really didn't allow manufacturers to run the vehicle much leaner than stoichiometric on the highway, because you'd run into emission barriers. And so when we get into emissions class in early summer, we're going to start taking a look at what those various emission components are, the terminology and what causes them to go outside of their boundaries. And one of the things that we look at a lot is NOx. And so NOx is produced under high heat and high load. So when we have an old school mechanical, the old school engine design didn't allow for a fluctuation in like air entering the cylinders, for example. And so we didn't have the ability to detune that engine on the fly. We couldn't add less air on your old pushrod cam and block engine because we didn't have any way to actually delay the opening or closing of valves on that engine. And so there was no need to have a wideband oxygen sensor when we didn't even have engine technology that could use it. And so it's kind of interesting that we have the ability to more accurately fine-tune engines before we had engines that needed to be more fine-tuned. The early narrowband oxygen sensors, they were not heated oxygen sensors. And as you read in the textbook and as we've discussed, oxygen sensors have to be at an operating temperature before they become accurate and before they can start functioning correctly. And so years after the oxygen sensor came out, they invented like the heated oxygen sensor. And so the heated oxygen sensor's purpose is to get the oxygen sensor up to temp as soon as possible, so that way the car's engine can go into closed loop. So closed loop operation is when the engine's warmed up, so we're atomizing fuel, but it's also when the oxygen sensor's warmed up. And so depending on the vehicle and what you're working on, the parameters that determine open loop switching into closed loop operation, it can be triggered by engine temp solely, but it can also be triggered by activity on your upstream oxygen sensors.